Hello everyone, my name is Niels Voorneveld and I'd like to talk to you about merging coeffect production into effect handling. This is recent work I've been doing with Tarmo Ustalu, which considers the situation where we have a program which can exhibit some effectful behavior, but which is run in some environment. And this environment can respond to these effects using some coeffects, some coeffectful behavior. And so in this response, it can be described using an interaction law that describes the interaction between program and environment and may yield some residual effects as well. Now, the nice thing about these interaction laws is that if we also have some extra information, so if we, for instance, have information on how to handle the residual effects, the effects that are raised after the interaction, and if we have a particular specification of how the environment produces the coeffects, then we can combine these two concepts using the interaction law to form an effect handler that handles the entire picture, so that handles the entire interaction between the program and the environment. And so in one shot, we have a way of describing the behavior of this entire scenario. So let's see in which situation we actually are. So all of you probably know what effects are, considering that this talk is featured at the HOPE workshop. And I want to zoom into a particular facet of effects. So in a specific situation where there are no effects, you can consider programs to be computations that are evaluated and produce at most one value, a particular value, according to some operational semantics that you specify. But in some cases, there might be some effectful behavior that arises either specified specifically by the designer of the programming language using some choice operations, or by some other situation that arises when evaluating the program. And this effectful behavior may alter what kind of result the program produces. So an example would be that certain choices are being made, and so the program requests some bit from somewhere. And according to different effects, these questions, the bits that they get might be resolved in different ways. For instance, we might have a probabilistic choice where we would get a random bit, so 50% chance for one bit and 50% chance for another bit. We might have some conditional choice where the bit that is gotten depends on some condition or some property of the environment. Or it might simply just ask a question of the user or of the environment. So asking for a particular input. And so in general, we might have represent a program using a decision tree, where here there are two choices being made. And depending on the choices, the answers, the bits that are gotten, we have different results, values that are produced. On the other hand, we have environments, and the environments may respond to these effects in different ways and influence the program behavior. Can consider two types of environment as an example. For instance, the environment may have some accessible global store that can be updated and looked at by the program. Or the environment may produce answers to queries of the program, and so provide data on request. And this behavior of the environment, or the ways that environments can respond, we specified using coeffects, and these coeffects specify basically two things: the resources that can be produced by the environment, like answers to questions, and if an environment does something, is interacted with, it may change. So the coeffect can also specify the ways the environment can be changed by the program. A simple example would be that the environment just is represented by a stream of data, so a series of inputs, basically bits that is produced. where for here it first produces a 1, then a 0 and a 0, and then a 1 and a 0 again. And then we can see this as represented with coeffects, where we can say, okay, it produces a bit, but after the bit is produced, the new environment will be symbolized by the tail of this tree. So these are the two facets of the coeffects that I mentioned in these 2 points here. And then when we combine the two, we can talk about interactions. And so once we have an interaction between program and environment, the actual result that the program gives, a particular value that it produces, depends on 2 things. Of course, it depends on which effects are invoked by the program, but it also depends on how the environment reacts to the effects, which is dependent on the initial state of the environment. A simple example would be when the program just asks for input of the environment, just asks for how to resolve a particular choice, and the environment is then represented by the stream. And in this case, because it's represented by the stream, first a 1 is produced, so that means we go to the right, and then we're here, and then a 0 is produced, so we go to the left. And so when this interaction is resolved, what we have left over is that the program produced V1, and we have this final state of the environment left over here, which is the tail of the initial environment. However, as I mentioned before, there might be, in more general cases, there might be some residual effects left over, or the environment might be specified using in a more complicated way using coeffect production. And so, in general, we will look at interaction laws between the programs and their environments, which might have residual effects, and which then, as I said in the introduction or at the very beginning, we will then combine using specification of how to resolve the residual effects and a coeffect producer that talks about how the environment reacts. And in fact, when we look at this way of combining, this merging effect, this coeffect production into effect handling, that way of merging the two gives us an equivalent way of describing interactions between monads and comonads, program and environment. So let us kind of zoom into the particular situation that we looked at. So first of all, what do I mean by effect handling? So in general, we can represent effects that may be resulting from a program using a monad. And this monad can be seen as, this monad is a functor in the category, and can be seen as a way of combining possible results of a computation. For instance, the monad can be a monad of binary decision trees, or it could also be the power set monad in the case of non-determinism. And so T of x, where x is could be seen as the object of return values, and T of x symbolizes then a program that after some effects produces a result. And then what we mean by effect handling is a way to extract from the program the actual result that we're interested in. So we look at the particular object of results, and then an algebra that extracts from T of x an element of x. And in particular, we want this to be a monad algebra, so it satisfies the unit and multiplication equations. Or in particular, for instance, this unit equation just says if there are no effects and resulting into a result, then nothing basically happens. We just retrieve the result itself. And we can see these algebras as implementing, retrieving some result from a program. We can see that it is in 2 different ways. You can see it as a direct result. If we directly handle the program and just kind of selecting a particular the particular result that is produced by returned by a program. However, in general, for instance, if we look at the power set monad, the distribution monad, we cannot directly handle or find the explicit result that we get from the program, because how do we select a particular one? We just get a distribution or a set. So an alternative way is to do a test on the results. And so what we look is a predicate on the results that gives you a certain degree of truth at the end, and then we handle that. So for example, when we look at randomized programs, what kind of predicates do we want to look at? A good idea is to just kind of ask yourself, okay, so in a randomized program, things are not just true or false, things have a certain probability of true. For instance, does the program produce an even number? Well, that's a certain probability. So the natural types of predicates that we look at in randomized programs are predicates that are valued by probabilities. And so results of tests would be given by this interval, real number interval here from 0 to 1. In randomized programs, we would use the distribution monad to combine all different results. And then the way to actually extract the expected probability would be using the expectations algebra here. So for instance, here, the question is, does this produce an even number? Well, 4 is an even number, so there's one probability of 1 that it is produced here, probability of 1 that's produced here, probability of 0 that's produced here. Now, if we take expectation over these weighted probabilistic choices, we can retrieve that the probability that this program here produces a real number is actually a half, or 50%. On the other hand, we have coalgebras that specify how what coeffects are produced by the environment. And so in general, we would look at a co-monad, which specifies which coeffects may occur. And what we do is then use a coalgebra to extract from an environment state the coeffects, how it will respond to different queries, things. So in this general situation, we see y as a set of environment states and dy as the coeffect, kind of the complete picture of coeffects that are produced by that state. And then the coalgebra as extracting from the environment state the explicit coeffects, coeffectful behavior of the environment. And we want this coalgebra to be co-monad coalgebra, so it must satisfy the co-multiplication conditions. So let's look at an example. So a simple example would be where the environment just produces answers to queries. In particular, it then produces an element of k, so a stream of elements of k. But the co-monad is given by this co-limit here, where it basically says which is basically given by this, each step has a copy of the current state. It has a potential response that is given by the thing upon getting a query, and the new state afterwards, which is this is isomorphic to this list here, this stream here. And then the coeffect cooperation can be split into two parts, as I said before. Given dy, we can extract specifically which response is given by the environment, and we have an operation that tells us what the environment will look at. What the environment will look, how the environment will look after this is given. And in this particular case, we can specify the coeffectful behavior using this co-free coalgebra on 1, where the carrier set or the states of the environment are given by D1, which is basically a stream of elements of K. And then we can kind of see what happens here. So if we have this stream of elements here, this state here, we can look at what the new element is that is given, which is A0, and we can look at what the stream looks at after the element is given. All right. So now what we want to look at is how do these, so we have monads on one side that represent the initial facts and a co-monad on the other side that represents the co-effects of the environment, and how do they interact. And this interaction is described using an interaction law, which was featured very recently in the LIX 2020 paper by Katsumata et al. And in this situation, we have a monad of initial effects that the program can raise, and a variable x that gives the possible results of a program. We have a co-monad for the co-effects that can be produced by the environment, which is then applied to a parameter for states of the environment. So y is not a state of the environment, it's a set of states of the environment. And we have another monad for the residual effects that may result from the interaction. And there are two types of effects that might be stored in the residual monad, which is some effects that were from in T but were untouched by the interaction, or you might have some effects that may result from the interaction. So maybe the program requested something of the environment which was not there, and then some error was raised, and this error would be a residual effect. And then an interaction law then specifies the following thing. Given some predicate on the X and Y, so a predicate on possible results that the program may give, and a possible final state that might be when the result is given, and a predicate on Z, where Z represents results of these tests that I talked before, for instance, probabilities. Given these, this can then be lifted to this interaction function, as you can kind of see, where you have a program, this effectful combination of results, this coeffectful combination of states, and a way to show how these interact and result into this residual monad structure here, these residual effects with possible results here. And this is an interaction law if it satisfies some unit and multiplication equations. The nice thing about this higher order representation of this thing, talking about predicates, is that we can easily get rid of any of the three parameters using a version of the Yoneda lemma by just substituting a certain structure. And in particular, for the purposes of this talk, we'd like to substitute the following thing, which is we'd like to kind of abstract away the notion of term, so the notion of result, which, because maybe in general you might have X might be of different types, so we don't want to consider this as the fundamental part of our interpretation. And so we abstract this away by taking the interaction law using, instead of X, predicates on state. So Z-valued predicates on state. And then we then have a function here where X is predicates on state. And then we substitute in this homomorphism predicate thing, we just substitute the application function. So this represents the fact that after we've gotten a result, a predicate result, what we do, we will just test it on the final state that we got. And if we have that, we get this natural transformation here of this nice form, T of Y to Z into D of Y to RZ. And this is just a different way of representing an interaction. And this then satisfies, again, unit and multiplication equations, which I will spell out in particular here, because it's a bit easier in this format. And this basically, the unit equation just says if there are no initial effects, then we just resolve it immediately, right? So we just resolve it in this way, where this function here extracts from dy the actual current state, then checks the predicate, and then lifts it by saying, oh, we just get that answer without any effects that are raised. And the other multiplication just gives us a way to sequence correctly all these things. So it says if we have this tower, this double layer of effects, if we just do in 2 steps the interaction and then sequence the things, then it's the same as sequencing first. This is just making sure that everything works well when we look at sequenced computations like higher order programs and such. So let's look at a particular example, which will be a running example in this talk. In this case, we have a monad of binary decision trees where some choices are made. And we ask for the environment to make some decisions. So it asks, oh, go either left or go right. However, the environment in this interesting example does not just give an answer 0 or 1, but it might also give intermediate answers, like elements from the real number interval 0 to 1. And so as a result, the choices cannot immediately be resolved. Instead, we still need to then use this answer from the environment to make a probabilistic choice. So, and so as a residual effect, we still have some weighted decisions that may be resolved. which could be, for instance, stored in the monad of distributions. And so the interaction can be specified in the following way, where if we encounter a choice, what we do, we ask of the environment what weight is given, and then we do a probabilistic weighted decision, a probabilistic, weighted choice to either go to the left and the right, and then if we go to the left and the right, then we use the new situation, the new state of the environment. So for example, if we have the initial state of the environment here, or initial environment E0, and it produces P0 and P1 with these new situations that we are new environments, intermediate environments, then if we deal with this probabilistic choice, where the leaves are given by predicates on state, and we do take E0, then we get this probabilistic choice, weighted decision tree left here. All right. So now, when I started this talk, I said that the focus of this talk was what happens if we take this interaction law and actually specify both what we do with the residual effects and specify how we can extract the coeffectful behavior from the environment state. So in this case, we have a specification of the interaction, and that then allows us to have a coeffect production morphism here, which is a coalgebra, and an effect handling for the residual effects here. And if because of this interaction laws of this nice form, we can do this composition, which basically gives us this algebra here. And in fact, this interaction law composed with this here gives us an algebra, a monad algebra on T, due to all the properties that all of these things satisfy. And the nice thing about this representation is that now we have one effect handler that handles everything in one go, where we have a program that has may raise some effects, and then we get some predicate on the final state when the program terminates, and it then retrieves a predicate on the initial state, which can be kind of interpreted as a weakest precondition. So this handles everything at the same time. For instance, in a running example, where Y is the stream of weights and Z is this probability, and we have this coalgebra and algebra given by the co-free and the expectation morphisms, then what we in the end get is this Y to Z is given by functions from the state, these streams here, into probabilities. And so we get a version of a weakest probabilistic precondition operation on environment states, which is very convenient in interpreting and verifying things about the interaction, verifying properties about the interaction between programs and the environment. So let us kind of take a step back and look at what actually happens categorically. So in a way, what it actually does is that the interaction law specifies a way to combine a coalgebra and an algebra into an algebra, as we've seen in the title, merging the coeffect production into effect handling to get a complete handling on T, which has certain properties. For instance, first, it's a functor, so it behaves nicely on morphisms between coalgebras and algebras. And as we've seen on the underlying carriers, this merging will do the exponentiation. So by this, I just mean that here we have the carrier Y, and here we have the carrier Z, and then the resulting algebra has its carrier predicates on Y, Z value predicates on states. And so that is a merge functor in general. And so the nice thing is that these merge functors are in one-to-one correspondence with our residual interaction laws between T and D, which is kind of the central theorem of this. So we have these two viewpoints. We have an explicit way to describe the interaction on a syntactical level, as it were. And we have a way to just the other side of it, which is the focus of this talk, which is completely behavioral interpretation of everything, which talks about merging both the behaviors of the residual effects and the behavior of the environment into the behavior of everything together. So indeed, as I said, this gives us bijection between interaction laws. And just for fun, I'll also give the inverse of this thing. So as we've seen, we can extract the merge functor from an interaction law just by composition. But given the merge functor, we can again retrieve the interaction law by discomposition. And what we do is the following. So in general, we might not have a coalgebra, a nice coalgebra and algebra for R. The only types of coalgebras and algebras we have in general will be the co-free coalgebra and the free algebra. And so that's what we do. So we apply the merge functor to the co-free coalgebra on Y and the free algebra on R and Z. This gives us this function here, where the carrier sets are dy and rz. And then we post-compose this just with this co-unit and unit operation. And this gives us back the interaction law. And this actually gives us an inverse of our function before, which can be seen, for instance, in one way by this diagram here. So here we, from an interaction law, we retrieve what the merge functor, the constructed merge functor looks like on the free and the co-free and the free algebra using the composition from before. And then using this composition here, we can then see, using the conditions on the interaction laws, the unit and multiplication conditions, we can then see that when we construct the merge functor and then the interaction law, we get back our original interaction law, given these conditions. All right, well, a nice observation that we can make from this bijection result is that in the inverse, as you saw, is we only use the co-free and the free algebras. So in fact, this bijection factor through the just the co-free and the free parts of these merge functors, where we specify this part, as I said, as the Kleisli Merge functor. So a Kleisli Merge functor on T, D, and R is given by this functor on the co-Kleisli and Kleisli categories on D and R respectively, using an algebra on T, which, like a merge functor, has similar exponentiation condition on its carriers, where it's not here explicitly the carriers, but it's the appropriate thing that we need. And we can see these Kleisli merge functors as subfunctors of normal merge functors. And what we actually have is that these normal merge functor by functoriality is actually completely specified by the Kleisli merge functor, the subfunctor, the Kleisli subfunctor. And that can be seen by this nice diagram here, where you can see that if we apply the merge functor on the general coalgebra and algebra, it's completely specified by what it does on a co-free and free algebra here. Because what we can do is we can do this composition here, where we start with unit, then this on co-free and free ones, and then post-composing with the algebra, the coalgebra and the algebra. That's what we can do. And then due to the functoriality of this and the fact that the coalgebra and the algebra are co-monads on coalgebras and monad algebras, hence they give monad morphisms and co-monad morphisms from the co-free and free into themselves respectively. And so it can use functoriality here. So everything is specified. The merge functor is completely specified by its Kleisli subfunctor. Now, as I've maybe alluded to before, is that this bijection can actually be extended to an isomorphism. Of course, then we need to know what is actually a morphism between two merge functors. We define these morphisms in such a way that they coincide with morphism between interaction laws. So we say that the morphism between the merge functor M on T, D, and R and M prime on T prime, D prime, and R prime is given by a triple of monad and comonad morphisms, T, D, and R, where in particular D is an opmorphism, because of, as we've seen, the domain of merge functors, such that it satisfies this condition here. So for any comonad coalgebra and monad algebra, this condition holds. So either if we do T and then we do M prime on the coalgebras and algebras, then it's the same as composing the coalgebra and algebra first with the comonad and monad algebra, and then applying them. And then this notion of morphism between merge functors actually gives us the fact that there is an isomorphism between the category of residual interaction laws, the category of merge functors, and the category of Kleisli merge functors. All right. One last observation is that when we got the final handlers, the merged handlers, that resulted from merging coeffect production into effect handling, we got an algebra at the end. We can also look at intermediate states. So for instance, if we just combine interaction law with a comonad coalgebra, what we get is a stateful runner, seen in a paper by Tomo in 2015, and which is something of this form. And here we see we got rid of the comonad here. On the other hand, we can also only deal with the residual effects using the monad algebra, and then we get another type of runner, which is a new observation. Then we get the D-field continuation-based runner of T for Z, which is the natural transformation of this form. And both of these must satisfy unit and multiplication equations. And both of these viewpoints give us, again, even another equivalent description of interaction laws. All right. For the end of this talk, let us look at two more examples to kind of more flesh out why this viewpoint of using coalgebras for coeffect production and algebras for effect handling, merging these two things using interaction laws actually gives us a very nice interpretation of properties of programs. So for that purpose, we look at two more examples. First case is kind of a very old example, which is a combination of probability and global store, where the initial effects are both probabilistic choices and lookup and update operations. Then as the environment, we implement a global store, so they can, so there's a global place where we can store some data, and so the environment can then respond to these lookup and update operations by providing the current state or updating whatever is in the store. However, it leaves the probabilistic choices untouched. So as a residual effect, we still have the probabilistic choices left over. And as I said, this interaction resolves global store operations using a coeffectful description of global store, leaves the probabilistic choices untouched. And then if we then use the correct interpretation, so the coalgebra for global store and environment and expectation algebra for the residual probabilistic choices, what we get using the framework is presented in this talk is we retrieve an algebra representing the weakest probabilistic precondition algebra, which in a way represents this, very nicely represents this complete picture of this combination of probability and global store, and is featured in many different places in literature. Another nice example, which is kind of a different flavor, is that of paywalls, where it's kind of different, because the program will always return the same value. However, when evaluated, it may request payment of the environment. And so that's represented using these paywalls. And so we have the co-limit of saying either produces a result or it requests payment and then will continue the evaluation. And classically, that can be given by either it gives a result after a certain amount is paid, or it will never give a result. It will just keep requesting payment. Then the environment is then given by how much money is there available. And so that can be represented using this comonad D here, which is also a co-limit given by this operation here, where either it's all fine, no payment is requested and just returns to the current state, or a payment is requested and can either say, oh, I don't want to give any more money, or, okay, sure, you have money, let's continue this interaction. And then we again, so use this coalgebra, again with carrier, as coalgebra, again use the co-free algebra over D1, where D1 just says how much money the environment is willing to pay. And then with only one type of residual effect, which is saying that is the error by saying, oh, the environment doesn't want to pay anymore. Doesn't want to pay for your paywalls anymore, basically, which can be represented using this algebra here. And so in the interaction at each paywall, the program will check if there's enough money, if the environment is willing to pay, and the environment will then pay it. And if there isn't enough money left, an error is raised. And so we can capture this whole picture using a single merged algebra, which has as carrier this. So it just says, if this much is paid, then it's good. If you have this much money, then it's good. But if you have, just kind of specifying which amounts of money is necessary for this to the program to give the right result. All right. So now we're closing. We're getting near to the end of this talk. So let me give this opportunity to kind of look at 3 different topics that can look at in the future and also is more convenient. As we saw a bunch of examples. You might ask yourself, why are they interaction laws? Like I've not actually shown why they satisfy the unit and multiplication equations. And in fact, if the monad is specified, this T monad is specified by this initial, specified by a functor as a limit of this form, then the R residual interaction laws between T and D are given by natural transformations of this form here, which just kind of specifies in each single step for each effect that's raised, how you resolve this effect. And this natural transformation is not subject to any additional equations. So this kind of gives you a functor, a comonad functor interaction law, subject to no equations, but still in one-to-one correspondence with our residual interaction laws. So this makes it very easy to construct many interesting examples. Another thing that I've kind of alluded to is the fact that are these merged algebras actually useful? Well, the nice thing is once we have an algebra that interprets the effectful behavior, we can lift predicates on values to predicates on computations that return these values using this simple composition here. And this can be used as a foundation for a quantitative logic, which can be used to verify properties of programs or specify properties of programs. In this case, kind of in these examples, in kind of Hoare style, weakest precondition style thing. In general, the logic does not look like a Hoare style logic, but you can formulate a Hoare style logic within it. But in general, as seen in a previous paper by me and Alex Simpson, you can see how these monad algebras can give rise to quantitative logics, which, if that satisfies an additional property of omega continuity, then in fact it specifies a congruent program equivalence for languages like PCF with effects, basically. And so this gives us a stepping point of giving a notion of program state equivalence using this interaction and this interpretation using merged algebras. And that is a future avenue for future research. And the last observation I want to say is that there's another thing we can look at, which is what's called the cascading of interaction laws, which talks about kind of a 2-step interaction. So you have an interaction at first, which may have some residual effects, but these residual effects may be dealt with another kind of parallel environment. And then we can combine these interactions together using a deconvolution construction of D and D prime. And that's also subject to future research. And on the behavioral side of algebras and coalgebras, we use then combining the coalgebras on D on the one environment and on the other environment, and merging these together into a coalgebra on the deconvolution of D and D prime. All right, and that's there we've landed at the end of this talk. Here's a list of references. So this is the reference I mentioned many times, the recent Licks paper, which talks about introduces interaction laws. Then we have 2 papers by me and Alex Simpson, which talks about program equivalence, and a paper by Tom about finite stateful runners. Thank you all for listening.